All right, so now I would like to introduce our speaker for tonight. Our speaker is Ryan Glaubke, and he will be talking to us about the oceans. So without further ado, Ryan, you can go ahead and take it away.
Yeah, I would love to. Let me share my screen here. Okay, hopefully everyone should see that. Yeah, this is great. Ria, thank you so much for that introduction, and thank you all for tuning in and for participating in trivia and crafts. This is actually my first late night, so I didn't know this existed before now, and it seems like a fun time, and everyone at the museum puts on does a great job in putting this together. So thank you all for putting it together. Thank you all for tuning in. I wish we could be doing this in person. I can see all your faces, but nonetheless, I'm excited to chat with you today about ocean circulation, quite literally the motion of the ocean, which is a cheesy title, I know, but it was too easy not to name the talk that, so I'm sticking with it. But today, what I want to talk to you about, let me just throw you guys out of my way there. What I want to talk to you about in general is how and why oceans circulate and why you should care about it. So if there's one thing I want you to take away from this talk about how ocean currents work, is there's a bunch of different ways the ocean currents work. Different forces drive different kinds of circulation, but all of these are tied together into one complex planetary-wide circulation system that's incredibly important for the oceans and planet's health. But I'm going to break this down into three pieces today. I'm going to start off with looking at the surface of the ocean, and then I'm going to start talking about how the surface and the deep oceans are connected, and then eventually take it to why you should care about ocean circulation, its impact on Earth's climate. So let's go ahead and start at the surface of the ocean. So this is a beautiful animation. I hope you all can see it okay at home. This shows the incredible mosaic of ocean currents and patterns that you get at the surface of the ocean. And there's such a rich diversity of features, from large circular oceanic gyres that span entire ocean basins to small whirlpools called eddies that spin off in all these different directions here, to oceanic rivers, both small, like off the coast of the US here, to large, all the way around Antarctica, that transport monstrous amounts of seawater all over the planet. And you can get all of these different features from three simple ingredients. And the first and most important, which was one of the trivia questions earlier, is the wind. So all of surface circulation is forced by winds to some extent. And Earth has prevailing wind patterns simply due to the fact that Earth's surface isn't evenly heated, right? We have the tropics, which are warm and great places to vacation. And then at the poles, it's really cold, where none of us want to go on vacation, right? And the winds are set up to evenly distribute this heat across the planet. Now, the planet's wind system, which looks a little different depending on where you're at on the planet, it imparts energy into the ocean that helps it move along. So if we take our hypothetical block of ocean water here and we blow winds over the top of it, the friction between the air and the water at the surface there is going to drag water along with it. And on top of that, the friction of the water between the water at the surface and then just below it is going to drag it along as well, but slightly slower the deeper you go down. And the best way to illustrate this is with a deck of cards here. So if you have wind blowing over the surface ocean, you push these cards along, and of course, the top card is going to go the farthest, but those cards beneath are going to get dragged along as well. And that's because of friction. But I'm kind of teasing you here. This is a simplified way in which the winds in the surface ocean interact. And there's actually more nuance in the real world. This was best illustrated by a guy named Alfred Ekman. He's a Swedish physicist and oceanographer that lived in the early 19th century, early 20th century, late 19th century. And in 1905, he set sail on a ship called the Fram in the North Atlantic. And while he was chilling out on the deck of the ocean or the ship, doing whatever physicists did for fun in 1905, he noticed something really weird. And he was watching icebergs drift past the ship, just like this. And he realized that the icebergs weren't floating along with the direction of the wind. They were drifting at about a 20 to 40 degree angle off of the direction of the wind. So that means the surface of the ocean wasn't flowing in the same direction. The surface ocean was deflected at an angle. And now, just like the surface, the layers beneath that get dragged along, as I showed earlier, they were being deflected as well. So it's much like taking this deck of cards here and twisting. Ooh, that was a bad demonstration. Here you go. Twisting the cards along with it. And, you know, this led him to come up with this crazy idea, which he named the Ekman Spiral. See, when you discover something cool, you get to name it after yourself, which we all aspire to one day, whether scientists admit it or not. But the weird thing about this spiral, though, it's really cool in theory, but if you think about the entire upper ocean and how water is moving in response to the wind, you get average transport at 90 degrees relative to the way the wind is blowing, completely in the wrong direction, right? You would expect the water to go along with the wind. It goes in a complete right or left-hand angle, depending on where you are on the planet. But why is that? Why is there this curvature in ocean flow relative to the wind? The answer to that is the second ingredient for our surface circulation, and that is the to the right in the northern hemisphere. I'll explain this in a minute. This diagram is in the northern hemisphere. Coriolis Force, that's our second ingredient here. The Coriolis Force, which actually isn't a force, it deflects ocean currents from a straight path because the Earth is rotating, right? So remember Earth's wind patterns here I just mentioned earlier. We see some curvature in the winds right here, and that's due to the Coriolis Force. In the northern hemisphere, those winds are being deflected off to the right, and in the southern hemisphere, they're being deflected to the left. Now, another way to illustrate this would be, imagine you're playing a really big game of catch, right? You're at the northern hemisphere and your buddy's at the equator, and you throw the ball to your friend. Now, if the Earth wasn't rotating, the ball would travel in a straight path to your friend at the equator, and they would catch it, provided you have a strong enough arm to get it to the equator, right? But because the Earth is rotating beneath the ball that you throw, it's going to completely miss your friend entirely. And to us on planet Earth, it's going to look like it has this right curvature to it, rather than what you would see from outer space, which is you throw the ball straight, but the Earth is just rotating beneath that thrown ball. So this is why the Coriolis Force is not actually a force. It's just a difference in perspective. But regardless, it has an important control on what features of surface circulation we see. And then finally, the third ingredient we have for surface circulation is probably the simplest, which is the shape of the ocean basin in which you're stirring up the ocean, right? When you're stirring it up, the shape of the bowl you mix it in, whether it's surrounded by a bunch of continents or by none at all, it has an influence on what your current patterns look like. So we take the winds, we take the Coriolis Force, we take the shape of the oceans themselves, and we put them all together, and we get an incredible array of surface ocean features all around the globe. So I hope you can see this video at home. This is just a quick world tour of some really cool features. Right here we have the Gulf Stream, which is a strong warm water current that brings waters up from South America and the equator, all up the southeast US coast, and eventually out into Northern Europe. This current is incredibly important for Earth's climate, and I'm going to talk enough about that a little later. But if we travel a little further south, down to the southern tip of Africa, we get the Agulhas current, which actually has a huge leak in it, right? The Agulhas sheds these huge whirlpools of warm, salty water from the Indian Ocean that leak into the Atlantic. That also has an important influence on Earth's climate. Now, if we creep up a little bit into the northern Indian Ocean, you can see these strong equatorial currents that are in response to the trade winds. But what's so unique about this region is that they completely reverse every year, which you can start to see right now because of the shifting phases of the monsoon system. Now, just a little bit further east, we can see the Indonesian through flow, which is a region of a bunch of islands where Pacific water can leak into the Indian Ocean. As we start to creep up a little bit, we can see the Gulf Stream's cousin here, the Kuroshio Current, which travels along the east coast of Japan there. And then eventually, way to the east of the Pacific, we get this monstrous equatorial circulation in the eastern equatorial Pacific, which pushes so much water back towards Asia that it brings up waters that supply, nutrient-rich waters that supply life, like you see in the Galapagos, such rich diversity of life. And finally, our last stop on this global tour here is the Antarctic Circumpolar Current. This is the largest current in the world. It's the only current that is not encumbered by any land barrier at all. So it can completely circumnavigate the planet all around Antarctica. And that makes it huge. It can build up so much momentum and speed and depth that way. And so that's what makes it the largest current in the world. Now, that's all really cool and dandy, but it's important to note that surface circulation isn't everything. There's surface in the deep ocean. They're connected by a planet-wide circulation system that one oceanographer named Wally Broker, he coined it the Great Ocean Conveyor Belt. And so in very specific regions of the planet, like the North Atlantic here, water can sink from the surface to the deep and then join a network of deep ocean currents that traverse it all around the planet. So what we're looking at here are waters sinking off the southern tip of Greenland, and then they get advected all the way down the Atlantic to the Antarctic Circumpolar Current. Now, these waters eventually spin off into the Indian and Pacific Oceans, upwell to the surface, and make their way back to the Atlantic to complete the journey once again. But what exactly are we talking about here? I'll play this again. We're talking about tons of water. Around Antarctica in particular, the flow there is around 100 sphere drops. Well, Ryan, what the heck is a sphere drop? A sphere drop is 1 million cubic meters of water per second. So for context, all of the flow of all of Earth's rivers combined is about 1 sphere drop. So we're talking about a lot of water that's moving through Antarctica down here. But we're also talking about a lot of time. It takes about 1,000 years for a parcel of water to go completely around on this conveyor belt. So it's a massive system moving massive amounts of water. But how does it work? Turns out all you need are 2 simple ingredients, heat and salt. So this is why we gave it the super scientific name, thermohaline circulation. Thermo meaning heat and haline meaning salt. So heat and salt cause waters to sink into the abyss and rise to the surface by changing the density of the water. So adding heat to the water increases the space between the water molecules, and so that makes it less dense. So warm waters tend to rise. Whereas if you cool a water parcel, that brings the molecules closer together, makes it more dense, and so cold water sinks. Now, fresh water isn't bogged down by a bunch of dissolved salt, and so it's low in density. Fresh water tends to float. Whereas if you add a bunch of salt to a glass of water, for instance, the density of that water increases, and so salty water tends to sink. So warm, fresh water is lighter than cold, salty water. And this is a picture from an experiment I did for a class recently where I poured nearly freezing, super salty water into a glass with warm and fresh water. And just look at that stratification. It's very, very clear where the warm and fresh water sits relative to the cold and salty water. So there's very specific regions on the planet where this density transformation happens. And so these are the cranks that drive the global conveyor belt. So one of these regions is the North Atlantic, where you have that warm water, warm, salty tropical water that's being delivered by the Gulf Stream up into the North Atlantic, where it loses a lot of heat to the atmosphere. So it's cooling. And because it already brings so much salt with it, that cold, salty water gets really dense and it sinks in these great chimneys down to 2,000 meters depth, which is roughly 6,500 feet, something like that. Now, another region is in the Weddell Sea off of the Antarctic Peninsula. And the formation of these waters is a little different. The waters are already really cold around Antarctica. In fact, it's starting to freeze. You get a lot of sea ice down there. But salt isn't incorporated when water freezes. That salt stays in the water that hasn't yet frozen. And so any water that sea ice is forming in gets saltier and saltier with time. So it's already cold, you're increasing the salinity, you get really dense waters in this region. In fact, the waters that form here live at the very bottom of the ocean. I should mention that the process of the salt being excluded from the sea ice is called brine rejection. That's our super scientific term for it. Now, these waters sink from the surface down to depth and then get circulated out and eventually into the Indian and Pacific Oceans, where they rise back to the surface. That's all well and dandy, but there's one region in particular where I think the upwelling of these waters is severely overlooked, and that's in the Southern Ocean. Now, the winds around Antarctica are so strong and they push so much water away from the coast that a lot of the deep water, 65% of all waters that occupy the interior of the ocean, come up to the surface around Antarctica. And it's an incredibly important place for the exchange of deep and surface waters. But when you look at it all together, this is Earth's circulation system. And a lot like our circulation system in our bodies distributes oxygen that keeps us healthy, the planet's circulation system, the thermohaline circulation system, is incredibly important for distributing heat, salt, carbon, nutrients critical for photosynthetic plankton that keeps the oceans and the planet healthy as well. It's also important for global climate. And one of the greatest examples of this is the Gulf Stream. So all of this water being funneled along the eastern coast of the United States and into the North Atlantic delivers 1 million power plants worth of heat to Northern Europe. And this is why the United Kingdom has such a mild climate, right? You go to London and you're not freezing your butt off, despite London being at the same latitudinal band as Calgary, Canada, where the temperature difference is like 10 degrees C colder. So this important influence that the Gulf Stream has on Northern European climate has served as an inspiration for Hollywood. I'm sure some of you have seen this Day After Tomorrow movie. It's a horrible disaster movie that I have a soft spot for disaster movies. And the whole premise of this movie is that the Gulf Stream gets shut down by modern climate change. You have melting ice around Antarctica that dumps a bunch of fresh water into the North Atlantic. And because fresh water is less dense than the salty water needed to create that surface to deep transformation, it turns the circulation off. And that heat is no longer delivered to, say, North America or the northernmost northern hemisphere. And that ushers in a new ice age. Now, of course, that doesn't actually happen. But like all disaster movies, they start with some kernel of a scientific fact before taking some creative licenses. And the fact here is that the Gulf Stream plays an important role in regulating the Northern Hemisphere's climate. But I would argue that there's an even more important ocean region for the planet's climate, and that is the Southern Ocean. So like I've said before, winds are bringing deep waters up to the surface all around the continent of Antarctica. And it turns out that that fundamental feature is really rescuing us from some of the worst aspects of modern climate change. These waters that come to the surface are great at absorbing heat and atmospheric carbon dioxide from the overlying air and storing them back into the interior ocean where they don't really bother us anymore. So the Southern Ocean has absorbed anywhere between 67 to 98% of all excess heat from anthropogenic global warming. That's human-induced global warming. And about half of all carbon dioxide emissions from human activities since the beginning of the Industrial Revolution. So this is great. Our warming and rising CO2 concentrations would be a lot worse, a lot more exacerbated if it wasn't for the Southern Ocean. But remember that this is not permanent. The Southern Ocean's helping us out, but it is not our permanent savior. As I hope you've picked up from our conveyor belt analogy, these waters eventually come back. It takes a long time, but they come back. And so while this is a really nice fact of our current existence, it's not a permanent solution. But what's interesting is that we know changes in ocean circulation in the past have had a huge influence on the planet's climate before human activity was ever a factor. And this is what I research as a paleoclimatologist and a paleooceanographer, which is someone who studies old climates and old oceans. And my specialty here is 20,000 years ago, when the planet was in the midst of the last of the great ice ages. Now, here you can see New Jersey just barely avoiding getting buried in miles of ice. And now what my job is, my job as someone who studies the interactive mind. Let's just cut out. Whoops, let me turn my light back on here. Okay, well, ignore me being in the dark. Now, for someone like me who studies the interaction between our climate and our oceans in the past, oh, there it is. We know that the ocean circulation system operated much differently than it does then than it does today. And we know this because the planet keeps a natural archive of its history within the mud at the bottom of the ocean. And so I and a bunch of my colleagues get to go out to sea and sample the sea floor and use the information we unlock from the mud to recreate what Earth's oceans and climates looked like a long time ago, and how they both changed as Earth climbed out of the last ice age and into the warm period that we live in today. And we do this by taking sediment cores, which are nothing more than a PVC pipe that we stick over the edge of the ship and poke holes with at the bottom of the ocean. We haul it back up to the surface. And that's what this video shows here with, okay, I'm back. This is what this video is showing here with us on our cruise 3 years ago in the middle of the Indian Ocean. Now we pull these cores up from the bottom of the ocean and we split them open, and they have these beautiful layers that are like pages in a book or rings in a cross section of a tree. And each layer represents a period in time. And as you travel from the top of the mud down to the bottom, you're traveling back in time. And what's phenomenal about these sediment cores is trapped within the layers of the mud are these tiny fossils called foraminifera. These are the amazing little creatures you were making with clay earlier. And what's amazing about these single cell creatures is that they build shells while they're alive, and the information about the chemistry of the water, which can tell us about ocean temperature, salinity, nutrient content, the size of the ice caps, all of it gets preserved within the shell's chemical composition. And with that information, we can piece together how different states of ocean circulation affected Earth's climate evolution tens, hundreds of thousands of years down to millions of years ago. Now, these shells contain fingerprints of what the planet looked like way back when. And it's my job and a bunch of other people's jobs to reconstruct that history back before we had scientists with thermometers and current meters to take measurements of the oceans in real time. And we can learn a lot from our past. And those lessons are going to help us navigate what's coming down the pipeline, help us navigate our future, a future that may seem uncertain now, but one that becomes clearer and clearer with every sediment core that we bring back up from the abyss. And so with that, I want to thank you all for listening to me, and I'm happy to answer any questions as well as share as many photos as you'd like to see from our time at sea. So thank you.
Thanks, Ryan. So if you go to the Google Doc, there are a lot of questions for you.
Oh, great. Let me get the Google Doc open. So should I read them out and then answer them?
Yes.
Okay, first question from Connie, who says, what was the most fascinating fact that you learned about the ocean? Oh, that's a big thing to choose from. Oh my gosh, I would say that the ocean is such a huge capacitor of heat and carbon. It's like a giant sponge that soaks up a lot of heat and carbon from the atmosphere, particularly in the Southern Ocean, but generally. That kind of buys us some time to make the necessary decisions we need to make in order to stave off the worst impacts of modern climate change. And so we can thank the oceans for that, but that comes with its own consequences. This is often referred to as the other CO2 problem, which is ocean acidification. We're removing a lot of CO2 from the atmosphere, and that's saving us from, too much warming. But adding CO2 to the ocean decreases its pH. It becomes more acidic, and that's what throws a bunch of calcifying organisms into whack. And of course, heat being absorbed by the ocean is really good for us as well, but you get these large marine heat waves that have a terrible impact on marine life. And so it's a double-edged sword, but it buys us some time. But that's a great question. So Ria's mom would like to know, have I ever been on a research cruise? If yes, which ocean were you in and what were you studying there? Yeah, so I answered that right at the end. The last research cruise I was on was in the Central Indian Ocean, really far away from civilization. We went out 3 years ago, and we're interested in studying how the Southern Ocean's circulation that I showed earlier, in the Indian sector of the Southern Ocean, how that changed over the last 22,000 years. Because as simple of a model as I showed for Southern Ocean circulation, it's actually quite different whether you're in the Atlantic sector, the Indian sector, or the Pacific sector. And the Indian sector is really understudied. Everyone goes to the Atlantic. That is, where everyone studied for long stretches of, oceanographic history. And the Pacific was the hot new thing 10 years ago. But now the Indian Ocean it's starting to look like that is a really important region. And we were the first to go there and get some cores. And so my PhD is trying to clarify that. And have we seen any sharks? I did not see any sharks, but we saw a lot of wildlife, which I can show brief pictures of here. Let me go to my slideshow and share my screen. You're going to make me share photos. So we saw a bunch of albatross, which are these large birds that live in the Southern Ocean. We had a few days where we were surrounded by a small volcanic island. We were sailing around a small volcanic island, and this species of bird you will only find on that small volcanic island, which is really cool. We saw a bunch of minke whales, and we saw a seal that was very friendly to us and would eat Cheetos that we threw off the back of the ship, except the bacon flavored ones. We had really disgusting bacon flavored Cheetos from Australia, and no one liked them. So we tried to feed them to the wildlife, and they did not like it either. But we saw a bunch of jellyfish, and then even under the microscope, you saw a great diversity of life in our samples. So these are just a few examples of that. So no sharks, incidentally, but a lot of, whoops, let me stop sharing here. A lot of great examples of marine life. Now let me go back to the questions here, sorry. Okay, do ocean currents affect sea animals? Yes, absolutely. Not only in transporting nutrients that are necessary for phytoplankton to grow, which is the base of the food web. But if anyone's seen Finding Nemo, the turtle scene in Finding Nemo, they're riding the East Australian current, which I didn't show in my video, but it's important for their migratory habits. And that there's examples of that all around the world. So absolutely, ocean currents like sea animals evolved to take advantage of ocean currents that exist in their habitat. So absolutely, the answer is yes. Do ocean currents always go in the same direction, or do they ever change? I think I touched on that in my talk. In the Northern Indian Ocean in particular, you get a complete 180-degree reversal of the current direction. And that's because in the summertime, during the monsoon season, you have a bunch of winds blowing from the ocean onto the Indian continent, and that's when you get a bunch of torrential rains. But in the wintertime, the winds shift direction and blow off of the Indian continent and onto the ocean. And so that complete reversal of the winds churns up the ocean and switches directions of the currents entirely. So yeah, it's the only place in the world that does that. So it's a really unique region. Why is the ocean water so cold off of California, even in the summer? Great question. So winds blow south on the Californian coast. So from Maine, or not Maine, that's the wrong coast. From, Washington, Oregon, down the Californian coast. And because of the Coriolis Force, which deflects water to the right in the Northern Hemisphere, those winds push water away from the coast of California. And when you do that, something has to rise to take the place of the waters you just pushed away. And so we call that coastal upwelling. And the waters that rise from the deep are really cold. They're not sitting at the surface of the ocean, soaking in all the hot California sun to warm it up. And that's really good for the kinds of sea life you see around California, because those waters are also really rich in nutrients. And so no matter what time of year it is, you get this coastal upwelling along California that keeps the coast really cold, which is the opposite of what you see, say, in North Carolina or Virginia, because the Gulf Stream is right there. You don't have upwelling, and the waters in the summertime are actually quite warm. It's sometimes it feels like bath water. I'm from Virginia, and when it's really hot in the middle of August and you want to go to the beach to cool off, the water isn't very cool and not really good at cooling you off. So yeah, great question. Can the circulation system shut down? What would happen if it did? So the answer is yes, or at least we think it shut down before. That was the inspiration for the Day After Tomorrow movie. About 14,000 years ago, there was the ice sheet that occupied the Northern Hemisphere during the last ice age was beginning to crumble away. And there was a large pool of meltwater on top of the ice cap that didn't make it into the ocean yet. It formed a great freshwater lake, and eventually that dam, that glacial dam that held it from the ocean, broke, and it dumped a bunch of fresh water into the North Atlantic. We think that was enough to shut down the ocean currents, and there's evidence that we had a brief return to ice age-like conditions. This was called the Younger Dryas event, 14,000 years ago. This was the inspiration for the Day After Tomorrow movie. Of course, that took thousands of years to happen rather than 3 days like the movie suggests. But what's interesting today, because the planet's warming and the glacial ice on Greenland is melting, there's some evidence to suggest that the ocean currents now are beginning to slow down. We don't know yet if it's enough to turn it off completely, like an extreme case way back when, but we know that it's going to have some influence on ocean currents, and people like myself are still trying to figure out what that means for our future. Suli would like to know, what are some changes we are currently seeing in the ocean as a result of climate change, slowing down ocean currents, marine heat waves because of all the heat that's been taken up, ocean acidification because all the CO2 that it absorbs reduces the pH of the water. And all of that has impacts on the abundance and prevalence, geographical prevalence of certain kinds of marine life. Yeah, so I listed quite a few there, so I hope that answered your question. Robin would like to know, what are the differences between the information we gain from analyzing sediment cores from land versus the ocean? Yeah, so sediment cores from the ocean tell us mostly about the ocean, right? Because the animals, the shells we're using to reconstruct past conditions, they were living in the ocean. But there's a bunch of terrestrial records that we can use, like lake sediment cores. where we can use pollen from plants that have fallen into the lake and settled into the sediments to reconstruct the prevalence of certain land plants on different continents. Like some of the most famous pollen records are from South America, Australia, New Zealand. There's also, you can use cores of glacial ice from Antarctica that can tell us about air temperatures over Antarctica. And what I'm trying to say is you can take records from land, and these records we generate from the ocean, and tie them all together to get a more holistic picture of what the planet looks like through time. Sue would like to know, are you seeing major changes in the water circulation, and would discontinuing fossil fuel help the water circulation? So the answer is yes. We're seeing significant changes in ocean circulation because of the warming that's happening right now due to human activity. Now, if we were to turn off CO2 emissions today, there is a certain inertia in the system to where it takes about 50 years for all of the CO2 to kind of evenly mix throughout the global atmosphere. And so warming would continue for another 50 years if we just turned off all power plants today. And there's warming associated with that as well. So probably almost 2 degrees C of warming if we were to stop today. That is accompanied by some measure of melting from Greenland. And we don't quite know if that would be enough to push the circulation system beyond a point that you can't come back from. This is what we call tipping points, right? And there's still a legitimate scientific debate about this. There was a paper that's come out recently that said, we're past the tipping point. And another paper that came out was like, we don't quite like the data you're using to come up with that conclusion. So tipping points are really tricky to find because we're running a real-time experiment on the planet's climate system, its oceans, its atmosphere, and we don't have direct analogs for what's happening with the planet today. The rate of change we see in the past is much, much slower compared to what we've done to the climate in the last 200 years or so. And so it's hard to come up with those tipping points, but the smartest people are working on it. I wouldn't consider myself the smartest people, but the smartest people are working on it. Do you have a favorite ocean current? Ooh, yeah, the Antarctic Circumpolar Current, I would say. It's massive. It's massive. It's because you have no land to obstruct that current, it just keeps going and going and going to the point where I don't know if you saw the cube of ocean I talked about earlier, but usually the surface currents are only felt down to about 200 meters or 600 feet of seawater. The Antarctic Circumpolar Current goes all the way to the bottom, all the way to the bottom. And what's great about that is you can use sediments as like an ancient current meter. Because the current reaches so far down, we can reconstruct how fast the current may have been flowing back in time just based on how much sediment it carries away with it, which is an amazing fact in and of itself. So yeah, I would say the Antarctic Circumpolar Current is my favorite. Let's see, Steve asks, favorite rock found in the ocean? Oh man, favorite rock. I don't know how many of you know about manganese nodules. They look like bulbous black. They almost look like small animal droppings, which is a little off-putting, but they take millions of years to form, millions of years. And they're sponges for heavy metals floating around in the water. And for a short time, the US government was toying around with the idea of mining them. The problem is they occur very deep in the ocean and they're very hard to find. When we were out in the middle of the Indian Ocean, we were poking holes in the ocean, getting all the mud and whatnot. We pull up one of our sediment cores and it has 50 manganese nodules in it. And so each of us got to take one home. And I think I have it behind me. I think it's somewhere up there. I can't find it, but yeah, we each got to take one home, which was really cool. So those are incredibly rare to find. Can you talk a little bit about what it's like living on a research cruise? What's a typical day on the ship look like? Yeah, let me pull up a few pictures that show that. I don't have to do the slideshow. I can just pull up the thing. One thing is it's a dirty job. There's a lot of mud involved and you get soaked in seawater. And as you can see from all of my friends here, it doesn't keep us from having a good time. The shifts are quite long. This is us in the computer lab of the ship here, working away, trying to find mud at the bottom of the ocean. Every day, no matter whether it's a weekday or a weekend, you're working 12-hour shifts, 12 hours on, 12 hours off. And sometimes you get really mixed up. Like I was working the midnight to noon shift. So my breakfast was dinner leftovers from the day prior, and my dinner was whatever they were having for lunch the next day, and I would go to bed at noon. It's a lot of hard work. This is a shot of us on the night shift. The best part about the night shift was all of the great sunrises we got to see. And these are just a few of the pictures that we got to take early in the morning. This is one of the volcanic islands right here that we were sailing around. And here's our multi-core, which helps us take a bunch of sediment cores at once over the back end of the ship. It's a great time. You get to see some crazy sights. This is me at the largest of the volcanic islands that we visited. And this was it at sunrise. Yeah, it's a really fun time at sea. It's a lot of hard work, and it can be really tiresome sometimes. I would say that, this cruise we did in the Indian Ocean was 2 months long, and that can be grueling when you're working 12 hours every day. But it doesn't stop me from wanting to go again. Actually, all of us are sailing back out in 4 weeks. We're going to Nova Scotia, and luckily this is only a 2-week cruise, so it's not going to be as taxing as the last one was. But it's a really fun time, and when you're surrounded by people who are interested in the kinds of scientific topics you are, and all of them are so much smarter than you, like my colleagues are, you get to essentially spend time on a boat, do hard work together, and talk about crazy ideas about Earth history and the oceans, and it's so much fun. So next question, can you talk about the research cruise you were going on in June? Yeah, that was, I just mentioned it. This is a trip we're sailing out of Woods Hole Oceanographic Institution in Massachusetts. We're sailing south off of the Jersey coast to take some cores along the continental slope just off the coast. So we're getting sediment cores from a shallow part of the water column, and then down the slope, sampling deeper and deeper, and then going back up to Nova Scotia and doing the same thing. And the reason you do this is because you can get yourself a 3-dimensional view of how the ocean might be changing with time. You've got cores from shallow depths to deeper depths, and you have a southern transect and a northern transect. And so when you generate the different records that we do, you get this cool 3D snapshot of how it changes with time. And so, yeah, it's going to be a great time. We're sailing on the RV Atlantis, which is the famous research vessel that houses the Alvin, which is the one that dove down and discovered the Titanic and discovered hydrothermal vents. And so it's going to be a great time. Let's see. Ree would like to know, are you seeing major changes in the water circulation and would discontinue? Okay, yeah, I answered that one. Layla would like to know, you may have mentioned this, but do you know how much of the ocean we've actually discovered so far? Yeah, so more than 80% of our ocean is unmapped, unobserved, and unexplored. And this is, oh, there go my lights again. We have a good idea of what the ocean generally looks like, but we don't have a high resolution picture of what the ocean looks like everywhere. And so anytime we go out on a research cruise, we bring along a bathymetric scanner to get high resolution pictures of what's beneath our feet. And this is what we did when we were coming back from the Indian Ocean cruise. Some scientists in Australia were like, hey, we have Perth Canyon off the coast of Western Australia. It's a marine protected area and it's super important for our regional economies. And we actually don't know what it looks like all that well. So can you please take a bathymetric scan of it and give us the data? And we did that on our way in and got some beautiful photos of the canyon. And so every day we're learning more about what the bottom of the ocean looks like. And sometimes you discover small seamounts like we did in the Indian Ocean that we tried to name after our colleague Harris, who discovered it, but it turns out you can't name features after yourself unless you're incredibly successful or you've recently died. So we got turned down, unfortunately. Okay, it looks like the last question here. How and why did you decide to study paleoceanography? By complete circumstance. I was doing my undergraduate research at Old Dominion University, which is in Norfolk, Virginia. And I was going through a program that was highly interdisciplinary. So it was earth sciences and ocean sciences, climate science. And I was specializing in geology and geochemistry, but I had no idea what you would do with that. The only thing I thought you could do was, mapping the seafloor, which it sounded cool, but it didn't. There wasn't a burning question other than what's the seafloor look like, right? And it took a new faculty hire in our department, Dr. Matthew Schmidt. Our department's pretty small, and I was an involved student, so I just went to his office and was like, "Oh, hi, it's nice to meet you. Welcome to ODU. I can't wait to take any classes you're offering." And he was like, "Do you want to hear a little bit about my research?" And I'm like, "Yeah, sure." And he told me about a sediment core he had from the Florida Straits, which are between Florida and some of the Caribbean islands. And he was like, "We can reconstruct temperature, salinity, and how fast the Gulf Stream was flowing during the last ice age." And I was like, "What? That's amazing." And it leveraged all of the geochemistry information I was learning in my undergrad. And so one day I read a couple of his papers and invited him to lunch and took him to my favorite coffee shop and asked him all of these questions about his paper. And to this day, he says I schmoozed him. But afterwards, I was just like, "Can I please be your graduate student? I want to go to grad school and I want to do this." And he said yes. So I stayed at ODU for an additional 3 years after my undergraduate. I got my master's. And I fell in love with paleoclimate, and I got to meet people on this cruise, the Indian Ocean cruise. And that's how I eventually came to Rutgers. So, and all of that was a bit compounded by where I was living at the time, Norfolk, Virginia, which is the second largest metropolitan city in the United States that is susceptible to sea level rise. Number one being New Orleans, right? So every day I'd had to fight flooded streets to get to work or get to class. And that really put climate change right in front of my face. I couldn't ignore it. And I kind of fell in love with this idea that we can learn lessons from our past to better anticipate our future. And that's the line that keeps me going in this kind of research. One more question. Not to get too existential, but based on the pics you shared on your trips, have you ever had a moment of awareness or feeling utterly insignificant to the scale of the planet? Oh my gosh, the planet's huge. Like I was showing you these pictures of this huge volcanic island with these huge sloping hills and sheer cliffs. Like you can't even see, these are huge waves that are battering against the cliff face here. This island is so small, you will not find it on most maps. And that's baffling to me. The fact that it took us over a month to get from Western Australia to, the midway point between Australia and Madagascar in the Indian Ocean. We didn't take a direct line there, but still it gives you a sense of the sheer scale of the planet. But at the same time, there's so many of us, there's a significant amount of people living on this huge planet that collectively we can have an impact on how the oceans work, how the atmosphere works, how warm it is in certain parts of the planet over others. And it's just, sometimes it can be overwhelming, I think. And that's why maybe it's useful to have a large community of scientists like we do in paleoclimate, where I work on this particular region of the Indian Ocean while someone else is doing excellent work in the Western Pacific, and we all go to conferences and bring the pieces together and put out reports like the International or the Intergovernmental Panel on Climate Change, the IPCC reports, that give us this overarching consensus of what we think is going on and how we think we can fix it. So yeah, the planet's huge, but at the same time, it's so tiny in that we're everywhere on this planet, and this is the only planet we have, and so we have to do the best we can to be the best stewards that we can be. And so I think that's the last question. So thank you all so much for the excellent questions. I loved talking with you all, and hopefully I'll be able to see some of you in person someday.
Thank you so much, Ryan. That was really great. And I agree, like everyone had really good questions, and you had even really great answers for everybody. So thank you once again for doing this for us. And thank you to our audience for being so wonderful and participating tonight. And yeah, so thanks again, and I hope everyone has a good night.
Thank you, everyone.